All right, so I'm going to take you on a little bit of a journey that has been a it's about a 5-year journey, and it's still ongoing. A 5-year journey in search of some assurance about the runtime systems on which we run so much of our software. Okay, so what are we in search of? This is an Arthur C. Clarke episode. So we're in search of verifiable, or in fact, more explicitly, verified implementations of on-the-fly concurrent garbage collectors. And you might say, oh, well, surely that's easy enough to do. But more to the point, I want to actually tie this to the underlying hardware and do this on modern processors with their relatively arcane, weak memory models. Okay, so a lot of these collectors make subtle use of expectations around the underlying memory system on the machines that they're running, because they don't want to over-synchronize things. Okay, so again, this is an ongoing project that I've been working on now for 5 years plus, and I'm picking it up again now as I've transitioned into my job in Australia. So we're really continuing with this. Okay, what I'm going to do here now is to go through the fundamentals of concurrent garbage collection with you. And by the end of the first piece of this talk, I will hope to convince you that these are hairy beasts that even the most proficient concurrent programmers stare at and wonder about the correctness of the implementations of these collectors. And so we want to actually try and put these complicated beasts on a firmer foundation with the eventual goal that we might in fact have a verified runtime system for managed programming languages. There's a broader context for that work as well. So I'm going to start by giving you a primer on basic GC techniques and terminology. We're going to be talking about principles which I hope many of you have already seen before. How many of you have heard or understood how a garbage collector actually works? A few of you. Okay. So the basic principles we'll be seeing, but I'll be then drawing those together into a more complex presentation of concurrent garbage collection. So what is a heap? A heap is really just an allocation space for the objects, if you like, the units of allocation in our programs. I'm going to talk about a heap as being a contiguous array of memory words or a set of discontiguous blocks of memory words. So it's not necessary that the whole heap itself be contiguous. Within the heap, I'm going to talk about what often people call objects to avoid confusion. The units of the elements of allocation in the heap will be contiguous groups of words within the heap, which I'll call a cell. And cells can be either allocated or free, or perhaps even wasted or unusable, depending on how well your garbage collector works. We'll also be talking a lot about what objects look like, or cells look like. We'll be talking about the fact that our program will have some number of references that it uses to refer to objects or cells within the heap, which we'll call the roots. These roots might be the values of references that are held in registers or in the local or global variables of the program. And an object itself will be broken up into some number of fields. Those fields may contain other references to other objects, such as the example that you see here with the last field there pointing to another object, or they may have non-reference values in them, a payload, if you like, for the object. These roots are the local or global variables of the program that will hold references. And of course, the objective will be to ensure that we keep around the values, or sorry, the objects in the heap that the program may access at some point in the future. Another thing we'll talk about is the distinction between what's known as the mutator, that is the actor or the program that's working on the heap that executes the application code and which is performing the allocation of new objects, and mutating the references of objects in the heap by modifying the fields and the roots. So there are two places where the mutator is going to be able to act. It's going to be able to load references from the heap into its roots, and also change or store references back into fields in the objects within the heap. And by now, I'm sure you're all very familiar with the idea that garbage collection is the notion that we're going to reclaim the objects that are disconnected from the roots, effectively those objects that are unreachable. This is really just an approximation on liveness. Of course, liveness, that is that knowing that I'm going to access an object in the future, is an undecidable thing, so we're going to use reachability as an approximation on liveness. If there is a reference that we can use to get to the object, if there are a chain of references we can use to get to the object, then we're going to assume that it is potentially reachable at some later point in the program. Okay, the other piece of the equation is the collector. The collector executes garbage collection code, and the job of the collector is to discover the unreachable objects and to free them, allowing their storage to be reused. So we're going to recycle that storage, recycle those cells for future allocations that the program might perform. Okay, so here is an example little program. It's a made-up programming language. I'm just emphasizing that we have some way of describing the layout of the cells in the heap. In this case, we're going to have cells comprising a value, which is an integer, and a pointer to another cell. So we might use this to build a list of values in the heap. And you can imagine that we have some set of global variables. These might be, some set of variables in the program. These might be local variables. They might be global variables. Most of the time in this talk, I'm going to be focusing on the issue when we have a thread holding references in its local variables to objects in the heap. Okay, so a simple little program. We've got these variables, which are references to cells. They're initially null. And we're going to perform some allocations and some mutations along the way. And we can step through the behavior of this program. So the first thing is we're going to allocate a cell with value 0 and the next pointer null. And then we'll allocate another cell with a value 0 and as a value 1 and next pointer null. Each of those will be held in variables A and B. We can mutate the object that's referred to by variable A to have a reference to B now, so that's taken the B reference and stored it in that field of the object that's referred to by A. And we can go ahead and allocate another cell with value 2 and stick it into the next field of the B referred to object there. And then we might, in fact, then set the local variable A to null. Now, at this point in time, you should all be able to see that there's some garbage in this program. Which is the garbage? What can we no longer reach? Yep? A. Well, it's no longer A, right? But there is the object that was formerly referred to from A. Yes, okay. All right, so there's an opportunity here, and I'm going to now describe a fundamental algorithm for garbage collection in a single slide. Okay, this is what's known as tricolor marking. So we're going to use some terminology here to describe the state of the collector as it executes with respect to a notion that it's going to color the objects. It's going to color the objects that are reachable ultimately to be black, and anything that's left behind that is white will be garbage. So effectively, we're partitioning the heap between the objects that are all reachable, which will be black objects, and the objects that are not reachable, which will be white objects, and we'll be able to reclaim those. Okay, so here's the collector code. We're first of all going to walk through each of the roots and pick up the value that's in that root variable. If it's not null, and if the thing that we're referring to is is a hypothetical piece of garbage, at this point we're going to say, oh, no, it's not. If it's white, hypothetically garbage, we're going to actually change our minds and say, no, it's actually not garbage. We're going to set it to a new color gray. This new color gray signifies the fact that we know it's not garbage, but that it still may have references within it to other objects we have to now consider. Okay, so we're going to first off just gray the objects that are referred to from the roots, and then we're going to mark from each of those objects. All right, so if the first field is null, obviously, we don't have much work to do, we're done. The second field, the B field, we load the reference there, and if the object that it refers to, if the value is null, which it's not, and the object that we've referred to is white, then we're going to set that object to gray. Now we're going to invoke the subroutine mark, which is going to go off and from that object mark further objects. Now, I've written this here as somewhat underspecified implementation as to how we represent the gray objects. This could be represented as a queue or a stack, but in this case, I'm just going to say, suppose there is an object out there that is gray, then our task at this point is to work through the fields of that object and mark the objects that it refers to, that it has references to. So for each of the fields in that source object, the source object here that has the value 1 in it and has the reference to the object with value 2 in it, we're going to load the field. If it's not null, which it isn't, and if the target is white, then we're going to set the target to gray. And at that point, we're done with that first gray object. At which point we can terminate that loop and set that object to be black. So there's an invariant here that a black object will only have references to gray objects in this particular implementation. We then go back and see if there's any more sources of gray in this heap at this point in time. And of course, there is that last object there. For each of the fields in that object, we're going to load the field. If it's not null, we're going to set the target to white. But in this case, it's null, at which point we are done, and we can set that object to black. Question?
Why do we call mark for each root instead of just once?
Well, so the roots are only made gray in this loop. So we're going to take each root. Sorry, each of the roots is going to be made gray, and then we're going to mark from that.
But why not mark all the roots that need to be marked with gray and then just call mark once?
Oh, we could just as easily do that. I've set it up this way for particular reasons so that I can have a particular ordering on the roots. That's all. But there's nothing stopping us from doing it, graying all the roots and then going from there. That would be fine too. There's some perhaps locality advantages to doing it this way, that we're marking from the most recently grayed thing in this case. Okay. All right. So there we have garbage collector in a nutshell in a single slide. But most importantly, I wanted you to take away this tricolor description, because when we get to questions of correctness in collectors, we're going to be reasoning about them in terms of the invariants that are set up with respect to these colors in the heap. Okay, so we're done with that, and of course the next step is to free up the garbage. So we're going to simply do a sweep through the heap, and everything we find that is white is going to be freed. Everything else will be black and will be then reset back to the color white. So you can imagine that that first cell, it's white, so we free it. We come to the next cell, it's black, so we don't free it, we set it to white. And the next cell is black. We don't free it, and we set it to white. Okay, so now what we've seen is a very concise description of what's known as a mark sweep garbage collector. The marking is setting those colors, shading the objects from white to gray to black, and the upshot is that we end up with a partitioning of the heap into garbage and non-garbage objects. We can free the garbage objects. Okay, so is this correct? We have some properties that we'd like to prove about a collector. Safety is that the collector will never reclaim live objects, or more feasibly, that the collector never reclaims reachable objects. That's a property we'd like to be able to prove. Another property that we'd like to be able to prove about collectors is that they eventually complete a collection cycle, that they don't get stuck. Okay, that they are able to get to a point where you're able to collect everything that is garbage. Now that's an interesting property when it comes to concurrent collection, because the mutator, the concurrent program that is executing alongside of the collector, may be doing things to undermine that progress of the collector. Imagine just it keeps allocating things and the collector can never catch up.
Sorry, so that property is called flag.
Yes. It's simply saying that the collector remains able to make some progress throughout its execution and eventually completes. So this is a temporal property. Okay. Now, I'm not going to talk too much about temporal properties. It is something you would like to be able to say about a collector, that it does have liveness properties, but most of the rest of this talk will focus on safety properties. Okay. So far, so good. Well, let's reason a little bit about this collector. There are some invariants that we can observe in this collector. At the end of each iteration of the mark loop, here's the mark loop here. At the end of each iteration of the mark loop, there are no references from black to white objects. Okay, so we start with a gray object, and we process all of its pointers to make them the objects that they refer to gray, so that object, when it turns to black, has no white pointers, has no pointers to white objects. And from that, we can say that any reachable white object must be reachable from a gray object. It's the gray objects that represent a frontier, if you like, or a wavefront in the progress of the collector to finding all of the reachable objects in the heap. So this implies that all reachable white objects will eventually be marked by this process and by pushing this invariant through across each step of the collector. Now, I'm reasoning entirely informally at this point about the correctness of this algorithm. Obviously, this is something that you would like to prove a little bit more formally. But we're going to defer that for now because I don't want to just prove abstract collectors. I want to prove concrete implementations of garbage collectors. Okay? But these are the sorts of invariants that we will use to reason about the correctness of a collector as it operates. All right, so far so good, I hope. Are there any questions about that so far? Relatively straightforward, I hope. This is now where it gets a little bit hairier. The motivation for incremental and concurrent garbage collection is that a collection cycle, if you are going to stop the program and prevent it from changing the heap while you do garbage collection, means that you're going to have a period of time where the program has to wait for garbage collection. Now, that length of time is going to be proportional ultimately to the number of live or marked objects. This means that users might see pauses in interactive applications, or that you might have a transaction server that has transactions that time out because of the length of time for the garbage collection. That means that you have a bunch of retries in transaction execution. Or you might have real-time tasks that miss deadlines because the time between this point and the end of the collection cycle is too long. So one way to reduce pauses in garbage collection is to use what's known as incremental or even concurrent garbage collection. And there are different ways to configure this. The first notion is that, okay, we're going to take that work, that garbage collection work, and we're going to split it up into smaller pieces. And then we're going to interleave the execution of the mutator program, the white pieces, with the work of the garbage collector. Now, that has some implications with respect to synchronization and coordination between the collector and the mutator that are very similar to what you get in concurrent collectors. So much of what I'm going to talk about with respect to concurrent GC applies in much the same way to incremental collection, where we interleave with the mutator. Now, the only thing being that these interleavings can be set up to happen at well-defined places in the execution of the mutator program, so that you can have established some known invariant at that point before you do the garbage collection work. And that ensures that you don't have garbage collection work injected into some operation that might cause problems for the collector. An obvious place to do this is at allocation sites. You could simply have the mutator at an allocation site say, actually, why don't you do a little bit of garbage collection work for me while I wait, but only do a little bit. Don't do the full don't go all the way to the completion of the cycle. You could consider how you might, yes, Arjun.
Something that you implied in the previous slide. So it's not that memory is being freed incrementally. It's just that the algorithm is being.
The algorithm itself is.
And then the black tree is getting free.
Well, I'm thinking of these as separate GC phases. There might be some incremental freeing that takes place as well. It's possible to piggyback freeing on the back of mutator operations as well, like allocation.
Okay.
What's called a lazy sweep. And actually, that's used to get the the complexity properties of the collector to be effectively proportional to the liveness. The live set is the length of time for GC. Because you can imagine sweeping is actually proportional to the size of the heap. But you can amortize that by splitting it up. Okay. Excuse me just 1 second. You can imagine that we might have a mutator that has a number of different threads running in it, but even if we're going to do that with respect to incremental, we're going to have these periods where the mutator threads cannot run. So you might have to stop all the mutator threads, do a piece of incremental work, start the mutator threads, stop the mutator threads, do a piece of incremental work, and so on. Still doing interleaving effectively. This is not concurrent yet. We could even perhaps do parallel incremental collection, where in fact what you do is at the periods where you stop the mutator threads, you in parallel do a bunch of garbage collection work. And you'll notice that as we do this, the total time on the scale across the horizontal axis is going to mean that the mutator effectively gets to a particular point in its execution earlier than in the previous slide, because we're going to push some of that GC work into being parallel. Still incremental though. We could, in fact, though, consider having the collector run concurrently with the mutator's threads. Now, what's known as mostly concurrent collection still has what's called a stop the world phase, a brief phase at which the mutator threads are briefly stopped while some portion of GC work to set things up is done, and then the mutator threads are restarted while the collector continues concurrently with the mutator threads. So there's still a possible pause being introduced. The mutators will see pauses at that point, but hopefully those pauses are relatively brief. And then so long as things coordinate properly as we go here, the collector threads can run in parallel with the mutator threads. Of course, you could have mostly concurrent incremental collection and all the variants. But ultimately, our goal is to have a garbage collection technique in which the mutator threads do not altogether stop at the same time, where you may have brief synchronization interactions with the mutators by the collector, sometimes what's known as a handshake. So the mutators and the collectors just rendezvous on a pairwise basis just to set things up, have a little handshake, here's how we're going to be, and then that mutator gets to run on, and then the collector goes and talks to another thread and says, oh, we're getting set up for GC, be prepared, and so on. And the important thing here is that there's no stopping the world. The mutator threads separately synchronize with the collector at the beginning of each collection cycle, but it's a very ragged synchronization. There's no single point where they're all stopped. Sometimes known as a ragged handshake. But after that, the mutator and the collectors, the mutator threads and the collector threads run concurrently. So that's a goal. In fact, that's going to be the emphasized goal of the collectors that I'm going to be trying to reason about. And the part of the reason this is interesting is because there's no real point in time where you could say all of the mutators are all on the same page with the collector. They come to that agreement individually. And of course, you could do this incrementally and so on. There's all those variants as well. All right. So far, so good, except not so good because there's all sorts of things that can happen that can go wrong here. And these revolve around the problem that we face when a mutator thread makes a change to an object that the collector has already seen and dealt with. Effectively, where a mutator thread makes a change to an object that's behind that gray wavefront. It's okay for us to make changes to objects ahead of the wavefront, that is to gray or reachable white objects, because we know that the collector is eventually going to get to them and is going to see that update, to see that change. But it's not okay for the mutator to go into the objects that are behind the collector wavefront and do things like inserting a reference to a white object into a black object, because it's going to break that invariant that we had that the black objects only ever perhaps have references to white objects. At least not without letting the collector know in some way. Okay, so this implies that if we're going to allow this sort of thing to happen, there has to be some sort of synchronization or some sort of informing of the collector that there's been a change. Yes?
You had this handshake at the beginning of the collection.
Mm-hmm.
Is there also a way for the collector to let the worker threads know that the collection is done?
Yes, there may be a need for a handshake at the end. It depends on the garbage collection technique, but it can be, some collectors do require a handshake at the end to let them know that it's done. Okay. So the real problem that we face here is that we don't want to lose live objects. Otherwise, we've got a broken collector. And there's a couple of conditions under which we can actually get into this situation of losing objects. We have to have a combination of these two conditions. The mutator has to store a pointer to a white object into a black object, and there's no path to that object from some gray object via white objects. So there's a combination of two things there that, in combination, these are the ways in which we lose objects in concurrent collection. From that observation, we can derive any number of mitigating techniques to fix the collection so that it never gets into a situation of having both of those conditions true. So we're going to see a number of techniques in a minute now which attack either condition 1 or condition 2 to ensure that we never get both of them applying. All right, here's one of the problems that we might see. So as I mentioned, we could have storage of a reference to a white object into a black object. So here we have a mutator with some roots, and let's assume that we've already marked from those roots. So we have one that's already been scanned and is black. We have another which is gray and is going to be scanned at some point. And you can imagine that the mutator might pick up that reference and take it and store it over into that black object. And then it could overwrite that reference with null. Perfectly reasonable things for a program to do is to move references around and overwrite other references with null. But at this point, if the collector kicks in and processes that gray object, it's not going to have seen that white object. Effectively, what we've done is we've stored the reference to the white object behind the wavefront. The wavefront is here. This black object is behind the wavefront. And we've stored that reference to the white object into the black object. Okay. That's one way to get into trouble. The other way to get into trouble is to hide what's known as a transitively reachable white object. So this is the condition 2 that we saw there. So we have a reference here that the mutator will follow this chain of references, pick up that pointer, and store it into the black object, and then overwrite a gray pointer, in this case, with null. So we've hidden this transitively reachable white object by breaking an indirect chain from gray through white objects. And that's along the lines of the second condition that we saw there, that we don't want to get in a situation where we cause that condition to arise. And then, of course, we'd end up again with a reference to white objects that would get freed up. Okay. So, question?
Does it also happen if you remove links from white?
Yes. Yep. Yep. It also happens then, yeah. Sorry?
Why is the problem if you have this hidden white object? Because it won't be collected in the next time.
It's not the reference in the white object that I'm worried about. It's the fact that let me get here. So we're going to take that reference and store it here, right? There, and we're not going to overwrite that with null. We're going to overwrite this one with null. So the reference that we modify is not the reference that we stored, and we're now left in the situation where we have a black object pointing to white, and when we're going to free up the white objects, and now we've got a dangling reference, a dangling pointer. Okay. Okay. So there are a couple of things that we can do to ensure that these situations never occur. One option is to preserve what's called the strong tricolor invariant. And this prevents condition 1. Condition 1, remember, says that we don't want to get into a situation where we store a white reference, a pointer to a white object, into a black object. And by preventing condition 1, we're going to ensure that there are never pointers from black objects to white objects. So there are a number of ways of doing this. And these are classical techniques. Guy Steele, back in the 60s, invented this one. And then went on to try and prove something about the collector that he wrote using this technique. And then he had to issue a correction to that paper because he got the proof wrong and there was a bug in it. Of course, he did not formally verify his algorithm. He just reasoned about it informally, or, well, semi-formally. And so these are tricky things. Even Guy Steele got it wrong. OK, so the basic notion here is that within this situation that we saw before, what we're going to do is when we store that white reference, we're going to retreat the wavefront. We're effectively going to take the black object into which we stored the white reference and turn it back to gray. And now the collector says, oh, are there any gray objects out there? If there are, yes, there are. I'm going to pick that up and I'm going to process it. So in this case, the mutator is allowed to have white roots, where the root mutator can follow this reference to the gray object, pick up that white reference, load that into a local variable, and then store it into the black object. And the action of storing is going to revert that black object to gray. And this preserves this strong invariant. Yes?
Don't you have concurrency issues if the collector terminates its cycle, then you turn it to gray afterwards? Like you started the collection?
So the collector's, here's the guarantee. The collector is not going to terminate its collection cycle while there exist gray objects out there.
Yeah, but you can have an execution in which you had the state before. You notice that your node is black, so you have to turn it to gray. Your thread is interrupted right now. The collector terminates, meanwhile.
Well, there's still this gray object here.
It could continue from there.
Okay. Now, what we're going to terminate this collection, we're going to have to go back to the mutators and make sure they have no white roots. So there is a termination condition here for this style of barrier, that to terminate the marking loop, we have to go back to all the mutators. This is an example of where you have to have some end state synchronization to ensure that you terminate. You have to go back to all the mutators and say, do you have any more white objects? And remark them if that's the case. Okay. So we actually would go back and have to terminate. We'd have to ask the mutator that doesn't have any outstanding gray or white objects. Okay. So we'd have to remark them from the roots. Okay, so reverting the wavefront now allows us to, that's fine, we can null out that reference, and we're going to now come back and obviously mark that one black, but we will see the gray one because they're existing gray, so we're not going to terminate the collection until we've finished marking that gray one. And at that point, we'll mark that black, and this will be grayed, and then that will be black. But interestingly, we are allowed to have the mutator pick up pointers to white references. It's allowed to hold those references. But to fix that, we do have to come back and resynchronize with the mutator. OK. Dijkstra, who also saw this problem of concurrent garbage collection as a particularly interesting problem in synchronization or coordination between concurrently executing actors, also tried to prove it. And there was indeed a bug even in his proof. So that bug was subsequently discovered, and he was able to reincorporate or fix the proof. All right, in this case, what we're going to do is, instead of regressing the wavefront, what we're going to do is advance the wavefront. And what we're going to do is to simply shade the target gray on storer. So again, the mutator is allowed to pick up white references. It can pick up that reference, take it and store it into the black object. But you'll notice that in storing it into the black object, it's going to shade that object gray. Okay. And again, this is fine. We'll end up deleting that reference. Doesn't matter because that object is gray, and we're good. Okay. Now, that strong tricolor invariant is in fact sufficient to get safety for concurrent collection. And so if you use either of those two techniques, then your concurrent collector will in fact be safe, subject to the synchronization that we might need at the end. There's another invariant, though, that is weaker. And this one attacks that second condition. We want to prevent condition, actually this should say prevent condition 2, by saying that every white object pointed to by a black object must be gray protected. That is, it has some protector out there that is gray that happens to be the head of a chain of white references to that object. And so long as that other gray object exists out there, then it's fine for that black object to refer to it. Now this is a strange property because it's essentially non-local. I'm saying I've got a black object, it has a reference to a white object, and there exists somewhere in the world a gray object from which that white object can be reached. And actually that's a very interesting property to try and reason about, because suddenly you have to deal with global knowledge of the system, if you like, in order to make a claim about this invariant holding. Okay, so how does this work? Well, one way to do this is with what's known as a read barrier. So this is going to be for a style of collection in which the mutator is never allowed to hold white roots. So when we pick up that white root, the collector is in fact actually required to make that root gray. So the minute that we pick up the white root, that has to be made gray. And when we store it into, I have to fix the transition here actually, this should have been grayed at the point that we loaded that white reference, so that the mutator doesn't have a white reference. And so when we store that reference, that object is already gray. Okay. Who can see why this might be a less desirable kind of barrier?
It looks very expensive if you actually never cut the references.
Yep. And what's more, it means that we have to perform a barrier on every read from the heap, not just writes. And reads are much less common than writes. Right? That's not to say that this isn't used. This technique is commonly used, but it does have this performance downside. That means that every time you read a reference from the heap, you have to make sure that the thing that is pointed to is not white. And if it is white, you make it gray. Okay, so we shade the target on load of the white reference. The mutator never holds white roots, and so it can never store a white pointer because it's never allowed to see one. Okay. There's another barrier, which is known as the deletion barrier, or what's sometimes also called a snapshot barrier. And the notion here is that what we're going to do is we're going to take, at some instantaneous point in time, we're going to pretend that we've taken a snapshot of the heap. And we're going to make sure that any operation that the mutator does preserves that snapshot. And in effect, what we're going to do is we're going to say, if you try to change or delete a reference that changes the reachability of an object, we're going to pretend that you hadn't done that. We're going to capture the snapshot that would have existed otherwise. All right, so again, this is an advanced wavefront technique. But what we're going to do is when we perform an update, we're going to shade the deleted target. So if we have a reference to a white object and that reference is deleted from some object in the heap, we're going to change that white object to gray. And this preserves that invariant that every gray protected object remains gray protected, perhaps by itself, by making it the gray object. So we can just run through this scenario here. Suppose we load that white reference and we store it into the black object. Note that this is allowing the mutator to see white references. And then if we're going to delete that reference there from the gray object, we're going to shade the target of that object gray. This preserves the invariant that the object that had been previously protected by this gray object is protecting that white object via a chain of white references. If we delete that reference, we're going to simply say, okay, your protector now is this object here. Okay? So you're just transferring the protection to the target in this case. Again, this is advancing the wavefront because we took a white object and made it gray. Again, if we proceed with this collection now, we're fine, because we'll eventually get to that gray object and process that, and this white object will be made black eventually too. Okay. Now each of these different barriers has different properties. Obviously, regressing the wavefront means that you're undoing the work of the collector, which has implications with respect to progress or liveness, right? If I keep doing mutations that cause the wavefront to keep being reverted, then the collector is never going to finish. The mutator can play a devil's advocate game and make it happen so the collector never terminates. So termination is a property that we would like to have, and we'd like things to terminate as quickly or in as timely a fashion as possible. The argument around termination is that eventually all the live objects become black. There are no more gray objects to process. That these barriers will only add to the wavefront. Marking only adds to the wavefront. The mutator barriers only add to the wavefront. And what's more, if we want to really make sure that things get to a brief conclusion, we can go ahead and allocate objects black. So they're never factored into the termination question for the collector. Right? The collector never has to look at them. We'll see in a moment that this has a slight wrinkle to it, which I'll talk about in a minute. Nice thing about the deletion barrier is that it means that we can avoid rescanning the mutator roots. It's okay for the mutator to hold white references because we know that those objects will eventually get marked because they're protected by a gray object, and we never have to go back and reconsider whether the mutator has some outstanding white references. So the mutator can safely acquire white roots after the snapshot. That's fine, because the snapshot is going to keep the reachability of the objects that we're interested in at the beginning of the collection. If we don't have that deletion barrier, then we're going to have to repeat marking from the mutator roots until no white roots remain, and that's the termination criterion if we don't have a deletion barrier. All right, so what's the wrinkle? If we're allocating black, which is a desirable thing to do so that we can don't let the mutator race ahead and allocate objects and prevent us from completing garbage collection. If we allocate black so that they don't have to get factored into this phase of the collector, this round of collection, then in fact the deletion barrier is not sufficient for safety. And here's the scenario. We have a mutator with a reference to a white object. It allocates an object black. It takes that reference, stores it into the black object. It hasn't deleted anything yet from the heap, and then drops that reference. We haven't changed an object in the heap, but we have dropped a root, which is a different thing, and that's not protected by a barrier. Okay. So this says that we have this one corner case that we have to worry about when we allocate black objects. Now, this might happen only in the case that we have an on-the-fly collector where there's some mutator out there that we haven't had a handshake with yet, and some other mutator has handshaked and said, oh, it's time to collect, I'm going to start allocating my objects black, and then somehow it communicates that black object to the mutator that we haven't yet scanned for its roots. So there are ways in which that black object can leak to the unscanned mutator that allows this situation to arise. Question?
Can you just mark any object gray? Like, if you are doing this when you're deleting the pointer from the white roots to the other objects, you currently have a pointer to that object. And
what you want me to do is to do the deletion barrier on the mutator. Okay. So now what you're telling me is that every time I exit a stack frame, I have to go through all the pointers in that frame, pretend that they're null, and then change all the things that they refer to gray. It's very expensive. Okay. We would like not to have any extra overhead for a mutator just to throw a root away.
But it only happens during garbage collection.
Well, but you still have to have that turn. You have to have the code in the mutator to handle that and turn it on and off as necessary as you go. So ideally, you don't want to do that. It's going to just add extra overhead. So it affects your throughput, your mutator throughput. I hope it's okay. Yep. Okay. All right. So as I said, this is a problem. and which means that we may want to have collectors where we're allocating black, not just have the deletion barrier to get the snapshot, but also to have one of the other barriers, the right barriers, turned on while that mutator thread has not yet been scanned. Okay? Yeah?
I'm actually not convinced by your answer, because you still have to do deletion barrier if the root was gray in the mutator thread, right?
I'm sorry?
If the root was gray, if at this point the root was gray, when you...
The root is gray. The roots aren't gray. It's either the objects are gray, either gray or white or black. So what do you want me to turn gray?
Yeah, right.
I can't do anything with those. Let's just assume that those are registers or something. We don't want to have to overload them with extra work just to move registers around or to drop them. Okay. So what this means is that for a concurrent collector that is going to have this property where I'm doing this on-the-fly handshake and some mutators still haven't been scanned and may contain white references like we see here, then we may want to have an insertion barrier or a write barrier installed while there is the case that there are white mutators, unscanned mutators out there. Okay. All right. So at this point, we get through it all. Oh, well, I'm just pointing out, though, that this doesn't matter for allocating white. If we allocate white, that's fine. Eventually, we'll get to scan that mutator and mark that gray, and then we'll catch the references. And similarly, if we're allocating gray, it's fine. Well, once again, once we scan that mutator, we're going to see the gray object, and we're good. Okay. So once again, safety in a concurrent collector can be reasoned about by taking these invariants and reasoning about the steps of the mutator and the steps of the collector together to enforce these invariants, to make sure that these invariants are enforced by the program and the mutator, by the mutator and the collector code as they execute. But the big question is whether we can believe these arguments for real in a concrete implementation in a setting where we have weak memory and where we don't want to have to over-synchronize our programs to ensure that every time they update the heap that they use some synchronizing operation like compare and swap or something like that on every mutation of the heap, which would be a problem. So the question that we asked several years ago was whether we can prove safety for an efficient production garbage collection algorithm that uses quite lightweight synchronization and has good throughput on x86, which has a relaxed memory model. Now, the relaxed memory model of x86 means effectively that when you issue a store to memory, that store takes some time to get out to the memory. It's put into a store buffer, if you like. And those stores are processed from that buffer by the memory subsystem lazily. It'll pick one up occasionally and put it into memory. You can cause all of the stores in the store buffer to be pushed to memory using a fence instruction. But again, fences are expensive. Ideally, we would have fences occur only in relatively infrequently executed pieces of the algorithm, of the garbage collection algorithm. And we'll see that the fencing behavior we have is actually conditional in the garbage collection algorithm I'm going to show to you now. Okay, so what I'm going to do now is going to transition to talking about proving safety for a real collector, which was originally described in PLDI 2010. We only got to prove it in PLDI 2015. And I'm unsatisfied with that proof because it's brittle and doesn't transfer to other fancy concurrent collector algorithms that I'd like to be able to prove correct. It's just a proof of one specific algorithm with one specific set of barriers installed into that algorithm. And I'd like to be able to prove it for different algorithms of different styles of concurrent GC. We also omitted some other details of the implementation, like the allocation sequence and so on, which would also be ideally a piece of the implementation that you would prove. Because allocation is something you want to be able to do concurrently with garbage collection and so on, and other threads. Okay, so I'm going to give you the brief overview of this collector, the bones of this schism collector, which appeared in PLDI 2010. It's what's known as a concurrent mark region garbage collector. I won't go into the details of what mark region means, other than to say that what we're doing is not marking individual objects, but regions of objects. If you're familiar with the IMIX allocator, has anyone heard of IMIX? Yeah. So IMIX is a region-based allocator, and so we're building on top of that style of allocation here. So that's why it's a mark region collector. But this collector is concurrent. It is on the fly. It has wait-free, constant time heap access. I'm not going to go into the details of that, but that's a nice property to have. It means that you can reason about how much it's going to cost you to manipulate the heap from your mutator program. And this fed into a design of allocation style that was allowing us to claim real-time properties for the collector and the programs that use it. The mark region allocator means that effectively allocation is linear time for small objects or without fragmentation, and it had good throughput. Now, our experiments were to show that we could have a real-time collector giving real-time behavior to mutator programs and still have good throughput, and in this case it was about 60% of the throughput of production Java virtual machines which are not real-time. But if you pull out those real-time pieces, you effectively get concurrent GC behavior that's very similar to that of production non-real-time Java implementations. Just to give you a sense of what the representation is, and we actually model this representation explicitly in our verification model. So we're actually down at the level of how the objects are structured. Every object has a flag that indicates if it is marked, and that flag is actually overloaded on a next field. So it's a specially marked pointer, which says whether this object has been seen yet and is gray, and if it's gray, it's on some work list. A single work list. There's a length field as well. No, the o.length field just tells you the length of the object. We also have a global work list. This represents all of the gray objects that the collector has yet to process, W. And then we have, for each mutator, we have a private work list, which is all the objects that mutator has grayed because of a deletion barrier executing in mutations that it's performed. And periodically, those mutator threads are going to have to handshake with the collector to hand over that private work list to the collector. And we can do that atomically, but just by appending the list to the global work list, and then the mutator is left with an empty list. But that handshake is just handing off that chunk of work to be performed. We have the standard mutator primitives. You can read from the heap, load a slot from an object. You can write to the heap and store a value into a slot in an object. And you can allocate objects. The collector and the mutators handshake in between these operations, never in the middle of these operations. So these operations are set up such that the check as to whether a mutator has to handshake with the collector does not get generated by the compiler inside of these operations. And so what are known as safe points are compiled into the program at backward branches, but not in the middle of these operations. So we know that these have completed when a mutator is handshaking. So if there's any outstanding work, it's not in the middle of doing that. The write looks something like this. I'm sorry, the read, I should have showed the read. Where's the read? Did I skip the read? Ah, okay. The read operation is just load the value. There's no barrier imposed on the read. The write operation has both a deletion barrier and an insertion barrier piggybacked on top of it. So you can imagine that we're reading, that we are writing to a slot I in object O. So the first thing we're going to do is to read the value, read the old value that's in that slot W. And that's the reference that's about to be deleted. We're going to mark that reference, effectively making it black or gray. Oh, sorry, effectively making it gray and putting it on our list. We're also going to take the value that we're about to store in the object and we're going to mark that as well. And then we store that value into the slot. Okay, so this has got both a deletion barrier. This is the deletion barrier here. We're taking the old value and we're marking it. We're taking the new value, we're marking that and then storing it into the slot. Allocation, I will just briefly describe as saying that it's doing some allocation of memory. It's setting the flag, whether the object is marked or not, to some global, the value of some global variable, the flag for allocation. And you're going to see that that changes over time. It's going to set up the data structure so that this object is not on any work list. Effectively, it's going to be treated as if it's black. And we're going to make sure that any initializing references have been stuck in there appropriately. Now, I'm going to assume for now that this is an atomic operation, so I don't want to get into the details of how we actually deal with interleavings within that allocation. Now, here's the collector itself. We have a global variable that tells the world what phase the mutator is in. Sorry, the collector is in. A collector will be idle, at which point the mutators really don't have to worry about things. But they're only going to know that by reading this global variable. And the reads to that global variable will effectively be racy reads, unsynchronized. Okay? The only synchronization that will ever occur is within these handshakes that occur. And a handshake will have appropriate fences in it to ensure that any updates that either the mutator or the collector have made to some of these global variables are actually in the memory. So they're going to be fenced. So the first step we're going to do is to, in the idle phase, we're transitioning from the idle phase to an initialization phase for the collector. So before we do that, we're going to flip the sense of the mark flag. Now remember when I described the collector earlier with the marks, the sweep portion, where we went through the heap and we changed all the black objects to be white, right? We freed up the white ones and the black ones we converted to white because they're now hypothetical garbage for the next GC phase. Well, here we're going to simply do that by flipping the sense of a global variable. So we don't have to scan through the heap and change all those flags. All we're going to do is flip the sense of this global variable. But we again have to handshake to inform the mutator threads that this change has occurred and to make sure that whenever they read that global variable, they see the new value of it. Because the handshake again has fence to ensure that that value is hit memory. In the initialization phase, where did we get to? We're going to set up for garbage collection at this point. We're going to change the phase of the collector again. We're now initialized for collection. And this is going to effectively turn on the marking in the store operation. So those marks are actually conditional. And then we transition to the next phase, which is a mark phase. At this point, both the store and the allocations are going to be marking objects. So we have the allocation variable set to be the sense of the mark flag. The allocation flag is now the same as the mark flag. We're in this marking phase. We handshake to make sure that everyone's up to date with these values of these variables. And then we transition into a series of handshakes with the mutators. We go to each mutator and we say, give me all of your roots, mark them all, and transfer them to me atomically so that I get them into my global work list. And we iterate through all the threads doing that. At which point, we fall into this section of the marking loop, where we're going to simply consider this work list, take things off the front. Those are our gray objects. We pull them off the front of the list. We dequeue them from the list. We shade the block in this case, because remember it's a block marking scheme. We shade the block and mark all the pointers that block refers to. And then we handshake to get some more work, and we keep iterating until we have no more work to be done. Now there's a subtle and interesting termination argument to be made here. How do I know that when the head of this list W is null, when the work list is empty, that there's no mutator out there that still has other work to be performed? And it's this handshake, this iterative handshaking. We have to go through a phase where we actually handshake with all the threads and get no more work to convince ourselves that it's time to terminate the collection. That turns out to be a subtle argument about correctness of termination in this algorithm. And then finally, we go off and sweep things. The sweeping phase takes place. Okay. So what does the mark look like? Yes. I wanted to try and keep things simple, Ben. Yes, I should qualify that for moving collectors, concurrency is even more interesting, because now you've got copies of objects and which copies are the mutators updating, and how do you keep those copies in sync? You can do that turns out to be kind of expensive. So I would advocate moving concurrent garbage collection is not a good idea. You shouldn't move things unless you absolutely have to because of compaction needs. Okay, so the mark itself. It has a sequence of conditionals here. And you can imagine compiling these in different ways such that portions of them are out of line and portions of them are in line. So you'd want the fast code to be in line and the slow code to be out of line, and we in fact have an implementation that does that. But the first thing we check is say, is the object marked? If it's not marked, then we have to do something with it. But first of all, we're going to check what phase we're in. If we're idle, who cares? We're not even working with the collector at this point. But otherwise, the collector is on and running, and we have to go off and do some things. So the marking of an object is achieved by an atomic operation. This is a compare and swap, where we are attempting to change the flag from not marked to marked, and we ensure that that transition occurs by checking that the result of that cas is not marked. That's the old value. The old value is not marked, and in fact, we won the race to do the marking. If in fact we run the race to do the marking, then we can stick this object onto our local work list. Question? Compare and swap. Fundamental synchronization primitive on x86 processors. Okay. What does it do? It takes a word of memory, in this case the flag word. It takes a value that you would like to store in that memory location. So in this case, we want to take a value which is we want to convert the value of the memory slot from not marked to marked. So we're asserting something about the old value, and we're trying to change it to the new value. And then we're making sure that what we saw in the slot atomically was what we expected to see here. This is what we expect to see. This is what we actually got. The result of the cas is what we actually got, and we're trying to make sure that what we saw is what we got. And if we were successful in doing that, then we know that the sense of that field has been changed to the value of the marked flag. And that's all done atomically in the hardware. Okay, so we're comparing a value for a location for an expected value. If it has that value, we get to install a new value, and we get back a success or otherwise of that operation. And the success is simply the value was what we expected to see. So effectively, what this is doing is we're trying to mark the object. If we come back the winner, the first to mark the object, then we get to go and claim that object for ourselves and put it on our work list. And that allows us to have this single chaining of gray objects together in the heap. The gray objects being chained together on a single linked list. This is all just messing with the linked list. And of course, this is a local work list, so we don't have to do any synchronization at that point.
Sorry, to ask a question, just to help me understand. So if you do that atomically, we end up with, if we didn't do that atomically, we would end up with, the object go on two different threads.
Well, and this representation doesn't allow us to have the object on two lists. It's only got a single pointer, right? So we're threading the grade objects through a single list header of the object.
So we just end up blowing the work list would sort of cease to be a list.
Yeah, yeah. Okay. So here's the transfer. It's what you would expect. We're synchronized. We're handshaking at this point, so it's safe for us to take the work list of the handshaking mutator and transfer it to the collector work list at that point. And then there's work to dequeue. It's the standard expectations for dequeuing from a list. Nothing special there. Okay. So I'm going to transition now to how we actually did this proof. And then I'm going to, whoops, you can't see that. Interesting. Mirror, that should do the trick. Okay. So I'm going to talk about the specific proof that we did for this particular collector, and then I'm going to talk a little bit more about, okay, where do we go from here to actually take this proof, which is very brittle and it's for a particular one artifact. How can we possibly even consider to generalize, which is the next phase of our work. By the way, this work was done in that location. That was the view from my front bedroom while I was doing this work. So just a little bragging about, you know, beaches and waves and all sorts of fun to be had. Okay. Interestingly, I'm clipping off part of the view. Single page. There we go. Okay. So my goal. I did this while I was on sabbatical before I had actually moved back to Australia. I was still at Purdue at the time. And my goal was simply stated to these guys, I've got this garbage collector, we've implemented it, runs really great. Can we prove it's correct? Because I'm not sure I believe it. So this was for me to feel better about this artifact that we'd built. So we wanted to verify this collector. And the basic result is what you would expect. It's a safety property. That is, everything that's reachable is a valid reference. It is everything that's reachable effectively is an object that is at the end of that reference, but it hasn't been removed. The reference itself is valid to use because there happens to be an object at the end of it. And we modeled our system as a single garbage collector, any number of mutators, and a subsystem component, which is what takes care of the underlying x86 TSO memory model. Okay, so we've factored the system in that way. So we've got this underlying system that takes care of those details and in which we have modeled the TSO memory buffers. Turns out that for when the system is a TSO model, there's always an object at every reference reachable from a mutator root under this model. So that's our safety property. Problem is also that I would like to be able to say, well, what about ARM's memory model? Well, we don't have that proof. We don't have that proof in this particular artifact. We only have the proof for TSO, but it's a question as to whether we can modularize the underlying memory models. So what are the challenges? It's highly concurrent. Memory is not sequentially consistent. I'll briefly state that in a moment. The mutators themselves may not be race-free. Yes?
Do you think your approach is incorrect on ARM? Do you think that the approach is incorrect on ARM?
Well, the proof is incorrect on ARM because we don't model ARM's memory model. So I'd like to think so. Okay, so that's the next phase of this project, which we now have a 3-year funding block to try and achieve. Okay, yeah.
Sorry if you already mentioned it, but could you say again what TSO?
I'm going to explain that in a second. Yeah. Okay. Now, I want to emphasize this one thing though. The mutators may not be data race free. So, how many of you are aware that a racy program in C or C++ is in fact a program with no meaning?
Sorry,
A program that has races in it in C or C++ has no meaning. Yep. The program could launch the nuclear missiles, blow up the world, feed your cat. All of those are valid implementations. Yes?
I think there are some data races that are not considered undefined behavior.
No, there are atomic operations which, if you use them correctly, give you defined behavior. But those are explicitly marked atomic operations. Otherwise, memory loads and stores are just, they have to be race-free. Okay? So one of the things that we really wanted to do here was to make sure that this algorithm was correct even in the face of buggy programs. Because the last thing I want to do as a garbage collector implementer is have a programmer come to me and say, my program's broken because your garbage collector's broken. Right? Now, I wanted to be able to say to them, no. If any brokenness exists, it's your brokenness, and it could be because you've got a racy program, but I know for a fact that my garbage collector is correct even in the face of arbitrary behaviors that might be introduced by racy programs. Okay, so you could be running a buggy program that has a race in it, which is technically undefined by C, but you still haven't found the bug yet. And I don't want to be the one who you complain about the bugs in your program for. And then, of course, we had to convince a proof assistant, in this case Isabel Hall, that in fact all of the invariants that I've been talking about up till now indeed do hold for the collector at hand. Okay, so I've already described the collector. You've seen all of this. It doesn't stop the world. It's weight-free for the mutators up to allocation. Allocation can be not weight-free because at some point you may need to go to a global pool, take a global lock, and get the space to be able to satisfy an allocation. We take a snapshot. We have this racing property with the mutators to mark the allocated, mark the reachable objects. You've already seen that in the description of the barriers. I won't talk about the fragmented allocation stuff. That's all about real time. But the claim was that it has predictable real-time performance, and you can look at the 2010 PLEI paper to see the arguments there. All right, so the folklore is, we've seen the need for cooperation. I've already described all of this for you. I'm not going to reiterate that. But I will talk a little bit about total store order. Okay, so we have, in x86 TSO, every core can be thought of as having a write buffer or write queue. When a processor performs a store to memory, that store doesn't go immediately to memory. It goes into the queue, and subsequent reads of that memory location by that processor, by that core, will go to the queue first. So it'll see the most recently written value that it's written, but other processors may not see that value yet. And it will take some time for all of those stores ultimately to percolate out to memory unless you use a fence. CASs are one example of the fence. So a CAS has the effect of flushing that store buffer. And there's some details as to how that's modeled. Don't take this bus lock seriously. That's not how it's actually implemented on x86 hardware. There's a coherence protocol that deals with all of this. x86 TSO is not sequentially consistent. You can, in the machine code, have data races, even though technically in C and C++, of course, those are disallowed. And the model itself, Peter Sewell is quite famous now for having come up with various memory models, including weaker ones than this, and validating them against real hardware. But that's only a validation. It's not a guarantee that the architects are going to actually respect that model in future. But this is about as close as we can get to having an understanding of the architecture. All right, so what's the data race look like? Here is an example. These are the ways in which programs that read and write to different variables can come up with some interesting behaviors. So if we start in this state where x and y is 0, and we want to have one thread setting x to 1, another thread setting y to 1, and then this thread reads from y into a register, and this other thread reads from x into a register, it is allowed for both of those threads to see R1 and R2 equal to 0. How can that happen? Well, the explanation with respect to a total store order is, or the write buffers, is that this write setting of the variable x in memory to 1 puts it into a store buffer, but it has still not hit memory. Setting this y to 1 puts it into a store buffer, it's still not hit memory. When this one reads y, it goes to memory and gets the value of y at that point, which is 0, because the one value hasn't hit memory yet, and the other one can read x and get 0. And so they can both see 0, even though they would expect perhaps to have seen 1. Okay. To fix that, you can put a fence in, but fences are expensive because they drain the store buffer. So you have to wait for the store buffer to get drained to memory. If we do that, though, we cannot observe R1 and R2 to be 0. And what you get is a sequentially consistent program, but significantly degraded performance. So if you want to make your program sequentially consistent, you just have to put a fence after every store. Okay, now, sequentially consistent programs are very well behaved, and there's a long history of work in verifying concurrent programs under the assumption of sequential consistency. Let's remember that they're being the progenitor of much of the description of what sequential consistency is and how to reason about it. Problem is that our mutators need not be data race free. We've made this assumption that they may have races. We still want to prove things about the collector being correct with respect to a racing program. And so we have to resort to general techniques for concurrency. We cannot use reasoning about things assuming sequential consistency. So for this assertion that we have that all reachable references refer to valid objects, that is objects that are in the heap, we have to worry about how that translates into a TSO setting. I don't know what the transition there was. I didn't really do anything. That's a repeat. The question now is, what does TSO do to our notions of reachability in this model? Because it can be the fact that the only reference to a live object is living in someone's store buffer. The collector inspecting the memory is not going to find that reference. It's perfectly reasonable that if I create a reference from A to B, that reference only lives here. And that the collector will not actually see that reference. That pending right is the only witness to B's reachability if we delete that reference to B. So, the insight of the correctness here is that whenever we do a store with our mark barrier, we're going to gray or put that object on a queue. And so every time we have something in a write buffer, we have to show that we also have that reference in one of our work lists. That's the invariant we have to carry through. So we're going to have to augment our notion of reachability to make sure that this always holds. Okay, so yes, the insertion barrier has already grayed these, so long as we can prove that always happens, then effectively what we're doing is we're treating this as extra mutator roots in our model. And all paths still go through the heap. These are roots, that's a root there for that reference from A to B. Who was talking about frames that last night? We were talking about frames that last night. Sometimes you've just got to churn the sausage, man. And making sausage is not a pretty sight. So, you can't always write a quote ugly enough to say what you want to say, so sometimes you have to rely on a giraffe filled with whipped cream. It's not a pretty picture, but it gets the job done. Okay. So we had to effectively deal with the mess that arises with this model and grind out for the invariants that I've talked about, these tricolor invariants, across the entire state of the system at each step that the system could possibly take, proving those global invariants. Now, it's a global invariant because of that non-local property of the deletion barrier. So you can't just say something locally about the state of the things that you have in a particular piece of the heap. You really have to have some understanding of the global state of the system, which is hard work. But we did a few things to make it easier on ourselves. First of all, I'm a programmer. I write programs. I don't write logic symbols. I wanted to be able to point at a representation of this artifact that looked like the code that I just showed you. Okay? So we devised a little language, a modeling language in which we could express the collector pretty much as code. We augmented a simple imperative language with a synchronous message passing model. And we used that synchronous message passing model to decouple all those components such that all the interactions between the components, the collector, the mutator, the memory is done by these synchronous message passing events. And what we end up with is a top level parallel composition, exactly as you see it there. We have a parallel composition of each of these components, including the system, and prove our invariance across that parallel composition. Fortunately, we can rely on some of those variables having local states. So every component has its own local control and data states. And there's no shared global state. So even though I represented some of those shared variables as being shared global state, what we're effectively going to do is we're going to communicate with the memory subsystem to update our local notion of what the value of the variable will be. And this gets us to a point where we can do some invariant reasoning that's effectively state-based. And to separate the programs, the invariants, and the proofs. I wanted a program I could point at, so I could think about what it means, what the invariant should be at that point. My proof engineer was able to then say, okay, I'll take that invariant and try to prove it across that program as it exists, and end up with a proof. So I believe the collector was correct, but Pete, who did all of the heavy engineering of the proof system, really had to push it hard. We have a system-wide program counter that encodes the GC's phase structure. And if you look at our paper, you'll see a very complicated diagram about what each mutator, what each piece of the system knows about the state of the garbage collector at those phase transition boundaries. And in fact, you get into situations where one person part of the system thinks the collector is in this phase, but actually it's moved ahead. And you might have two mutators that have different views of where the collector happens to be at any point in time. So you see this sort of, you throw in mutators over the fence of these handshakes, And at some point you get them all across that point, and then we know that the collector is either in that phase or has moved on to the next one. And then you try to get them on to believing that the collector's in the next phase. We did use data race freedom where we could, and sliced the program with respect to the variables that are not data race free. So we really focused where the interferences could possibly occur that we couldn't reason about with respect to race freedom. And we ultimately have very fine-grained assertions around those object marking operations. And that's where the heavy lifting of the proof was. And all of that's in Marrow logic, and we were able to make use of Isabel's ability to search for parallels for choices about how to proceed. So, first thing to take away, if you're a verification person, this is probably not the one way you want to do things for arbitrary programs. We were dealing with a single artifact that we wanted to come up with a proof for. And this is not something we necessarily generalize or scale even to arbitrary programs. We had deep, intimate knowledge of the collector and how it worked, and we had deep, intimate knowledge about the invariants we wanted to prove about the pieces of that code. It helped us to discover the invariants though as we went. And if you're a theory person, you come back and say, oh, why didn't you do the pseudo reduction theorem or something compositional like rely guarantee or separation logic? Because that's great, right? Shared variables that we can bring is blah, 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 blah. I have yet to see the theory concurrency people prove an extensive system using any of these techniques. They work for small examples, but they don't scale yet. Maybe they'll invent a scale technique. If they invent one, I'll be glad to use it. But right now, we were just dealing with global invariants and simple state transitions. And it wouldn't have helped, because we had to discover the invariants ourselves as we went. We cheated a little bit in the model. The model isn't the exact faithful replica of the actual collector. Minor things like the grey parts are not subject to TSO. Memory, we did not model the underlying allocation structures. We kept the ragged save points very abstract because those are ultimately implemented at some level in the operating system. And we assumed that each mutator GC is running on its own core, they're not sharing calls. It's possible that we can tackle some of these things with some madness or refinement techniques. And I think that's going to be the direction we'll be pushing in for our next group.
So why is that relevant? Really, that each one goes on for?
I'm sorry?
Well, why is it relevant that each one runs on its own core?
Well, there's questions of what's shared. So we had this, yeah, you'd have to prove that you don't share certain cache state and stuff like that, but obviously, yeah. So, where are we headed next? Well, as I kept saying, I'd like to actually have a family of concurrent collectors where we can modularize pieces of them and with refinement get down to more concrete implementations like this particular one. I don't want to have to reason about x86 TSO or ARM relaxed memory or blah blah blah. I'd like to come up with a fragment of the C11 memory model. Not all of it, just the pieces I need to build a garbage collector. And at this point in time, we're looking at what's called a relaxed acquire release fragment. Okay? So none of the other weird things that get you out of thin areas and all that sort of stuff. And if we can satisfy ourselves that we can use those fundamental primitives to build our collector, then we at least know what the compilers are expected to be transformed into. I'm not going to prove that those compilers are correct. So, yes, I say here something more executable. It's not clear that we're going to get there. I've been waiting for the last 5 years for the memory model people. I can name names. There's at least 3 groups or 4 groups in the world who are working on memory models. They crank out at least 2 papers a year on the latest variant of memory models and operational semantics, axiomatic semantics, supposedly compositional semantics. I don't think we've got to the point where we're actually going to have something that's executable. I'm not even clear that we're going to have something that's compositional, accepting insofar as we can have abstract and then refine down to more concrete. Liveness result. This is the notion that the system makes progress, that it doesn't get stuck. It's something that we did improve. And there are other things like making sure that the heap isn't mutilated in some way where bad things happen. We didn't prove that either. And I'd be happy to talk further. So just some takeaways. TSO is actually a pretty clean model. It's going to be an interesting question as to what extent the more relaxed memory models, the weaker memory models are going to be just a bridge too far. But that's part of our challenge that we're setting ourselves. It's been carefully constructed, this collector, so maybe we just got there because it was well thought through, or because it built on established principles for correctness. Scalability, we certainly want to get away from worrying about data races if possible. And the other thing is that we don't really have a handle on performance at this point. There's no real way for us to say anything about what it takes to execute a particular instruction sequence or something in terms of its worst case execution, which in a real-time setting would be actually nice to have. And of course, ARM and Power are more complex. So I'll finish up there.
Thanks. We have time for a couple of questions.
Yes, you're done.
I say, screw correctness, give me performance. Actually, that's just a question. What do you think the performance sort of ceiling or floor is for concurrent collectors? How much more can you get?
Well, we have examples of concurrent collectors where you get reasonable throughput rate. So I don't know, take your favorite Java concurrent collector, how does it compare status of the world market speed? They're pretty reasonable these days.
Is it 20%, 30%?
I think it's sub 20%. You lose some of the real-time properties, of course.
Yeah.
But yeah, so you can get another 20%.
They also have emergency action rules and things like that.
Yeah.
So it depends on how much footprint you want to go on.
Yeah. It's the usual trade-off memory for speed.
Any other questions?
Yeah.
Does life get better if you have only one mutator, or?
Life? No, it doesn't really. No, it's one mutator is as bad as many because of the interferences are all the same. It's just whether you've got multiple mutators banging on things or not.
Okay, let's thank you. Thank you very much.